base pairs. So there's A, C, T, and G, and a code. So like AGG will code for an amino acid, and ATC will code for another amino acid. There's actually redundancy in the code as well. So there are 64 combinations, but only 20 of them are used actually. So it's kind of, and that's interesting as well. But what you find is the first one usually codes for what's called a precursor, so the chemical building block of that amino acid. The second one usually codes for its response to water. So is it hydrophilic or hydrophobic, which is basically to do with the geometry, so the orientation of these molecules and how they orientate within the scaffolding that water provides. So actually you see that you can see where the origins of the chemistry in the code. So it's not just a code. They are chemical reactions, and they are coded for chemical reactions, and they are coded through it via chemistry. So it's a very chemical thing. And so you wonder whether, and these amino acids are not very complicated, they're not massively complicated molecules, so you wonder whether actually, pretty much, it's the simplest way. But what's actually thought is that probably the 2-bit code that codes for 16 amino acids was probably the first bit. And indeed, the 16 most common amino acids that go into proteins are coded by the first 2, and all the redundancies in the third. So it looks like the third one was probably a later addition that allowed a bit more flexibility and actually some robustness against mutations and things actually. So probably those 2 things, you might think maybe you'd get similar life elsewhere.
Just at the very, very base of it, yeah.
And then obviously then the complex, I mean, then you go on to talk about complex life, very different. I mean, there are lots of things that look like coincidences that led to, for example, a complex cell, the eukaryotic cell. That's a chimera, undoubtedly. It's undoubtedly the case that a bacteria, probably a bacterium and an archaea, these 2 simple forms of life, got inside one another, one way or the other, and that gave you ultimately the things called the mitochondria, which so they're bacteria, they're symbiotic bacteria that got inside, and they still are. They've still got mitochondrial DNA. These loops, they're not. It's a symbiont essentially, which has been carved down over the years into just doing a job, which is producing energy for the rest of the cell. So these look like chance events in the evolutionary history of life. So you'd be surprised if you had the same eukaryotic cells as prokaryotes, the same, chloroplasts inside photosynthetic plants, which again are symbionts. So, but the DNA thing, you wouldn't. It'd be interesting actually.
Where do you sit on that idea of life may be common and may arise wherever the conditions may give rise to the possibility of it, but complex life is much more. It's a whole different matter, isn't it?
Yeah, I mean, because the history of life on Earth is it was simple for a long time. By simple, I mean literally bacteria.
Well, 90% of the time of the Earth, wasn't it?
Well, yeah, I mean, the eukaryotes, I think, was a cell 2 billion years ago, something like that, give or take a lot. but complex life is the Cambrian explosion you look into, which is 550 million years ago. So 550 million years ago, before that, there was nothing much at all. Very complicated. And suddenly you get this explosion thing within a few not long at all, hundreds of thousands of years. You get eyes and body parts and things. It's probably to do with oxygen content in the atmosphere, maybe. You see the oxygen rise very quickly at that point.
I mean, yeah, well, once plant life started, that's when it all just started rolling. I mean,
but that's geology. The oxygen content in the atmosphere is as much to do with geology as it is to do with photosynthesis. So, so you have a very complex interaction between life and the planet in order to get complexity. But in order to get the initial bit, it's looking like, I think people begin to say, no, that's deterministic. That's just biochemistry that occurs anyway you get the right conditions.
Eyes is probably another example of that sometimes there are only a certain number of solutions to the same problem. We were saying with DNA coding, so maybe using core bases, they're doing different designs, but they've all ended up looking roughly the same, which is the eye, and they've come from different parts.
Absolutely, yeah.
Have you read Dawkins' Greatest Show on Earth?
Yeah.
He's great, isn't he?
Well, we also looked at, in the series, we looked at an octopus in some detail in terms of the evolution of the eye, because if you look for a common ancestor between us and an octopus, it's before the Cambrian explosion 600 million years ago. So there's no brains, no nervous system, no eyes, nothing. So that's evolved completely. It's as alien as you get, essentially. But it's very similar. And in fact, the eye uses very similar proteins and vitamin A bonded to the protein, essentially, to make something called rhodopsin. It's roughly the same in terms of its interaction with light.
So maybe there are only a certain number of solutions to common problems, like light collection and interpretation.
Yeah, although the common ancestor probably had these rhodopsins, we think. There's an algae called Volvox that has rhodopsins in it. And you have the common ancestor doing as an algae, and they're along like cyanobacteria, actually, 2 billion years ago or something. So probably you see an echo of the common origin in the eyes. It's really interesting, actually. I've gone forever about biology.
So you've done a crash course on biology now?
Yeah.
You feel you could lecture on this now?
Yeah, I don't know. I should say
You just talk fast enough, and
I'm
then
lecturing
no
at
one
the
will
moment
interrupt.
on quantum and relativity for the first years at Manchester. So, quantum and relativity question.
Okay, Graham, do you remember your question? Would you like me to hand over to you?
No, I think I know it. What is in your background that has generated such enthusiasm for astronomy? I mean, did it come from your parents, or come through a teacher, or through a rock band, or?
I mean, astronomy, I can't remember. I've always been interested in it, and I think it might be linked to the Apollo missions, because I was born in '68. And so I don't really remember, but I watched them apparently, and my dad was interested.
Yeah.
So I think it probably came from that. But then the thing that reinforced it really was watching Cosmos, I think, Carl Sagan's series when I was 12. And then, 13 episodes over 13 weeks of that. And once I'd watched that, then there'd definitely know that's what I'm doing, without doubt.
Yeah.
So I think it was reinforced by Sagan.
Yeah.
The big one. But I think Apollo, actually. I got on Stargazing last year. I interviewed Gene Cernan, which was just fantastic. The last man on the moon, and also it was Apollo 10, wasn't it? So Stanford Cernan and Young was Apollo 10, and then Apollo 17 was commanded. I think
With the first scientist on board.
with the Schmidt.
Yeah, Harrison Schmidt.
So I think it was Apollo 10, Apollo 17. There was actually, I've met him before at the Royal Society in London. I'm a research fellow with the Royal Society as well. They invited me to an event, and it was Cernan, Lovell and Armstrong on their way back from the Gulf. They'd been in the Gulf with the US troops, and they were coming back to London. And we had them for an hour like this. There were about 40 of us in the room. And